Hi, everyone. Let's quickly walk through how to use DYNAMIA-AI platform to manage our GPU resources. The main goal of this platform is to help us utilize GPU resources more efficiently and intuitively. Okay, now inside the platform, the first thing we see is a cluster list page here. Here's a default local cluster here, which is the local cluster that comes with the platform deployment. If you manage multiple clusters, they'll all be displayed here uniformly, providing a unified view for multi-cluster compute power management, which is very convenient. Let's click into local cluster to take a look. This is the cluster overview page. Here's some basic information here, but the key parts are these statistics on the cluster as total resources, like how many GPU cards there are, the total compute power, and total memory. Below that, we have charts showing resource allocation and usage trends over time, giving us a quick health check of the entire cluster. Next, let's switch to the node list. This lists all the nodes within the cluster. Besides the basic info, pay attention to these donut charts here. They show the GPU compute power allocation and actual usage rate for each node, as well as the GPU memory allocation and usage rate. This is incredibly helpful for quickly spotting resource bottlenecks or underutilized nodes. Let's drill down into node 1 for details. From this node's workload distribution chart and the more detailed GPU resource allocation and usage information below, we can see, this is already a workload on this node, but currently it doesn't seem to be actively using GPU resources. All the details are clear at a glance. All right, let's head back to the workloads list page. Here we can see the existing workload we just saw on the node. The list page conveniently shows associated monitoring metrics directly. Of course, you can also click in for more detailed monitoring data. This represents the full lifecycle management of compute workloads. Creation, running, and monitoring are all made easy. Now let's create a new workload. Click Create, enter a name like Demo0, and select a namespace. Notice how after selecting the namespace, the resource quota usage associated with it displayed below for CPU memory, GPU compute, and GPU memory. Let's switch to the test namespace to see the quota usage updates accordingly. This design greatly helps with resource planning and isolation. Next, fill in the image address. For GPU type, we support old cards, eGPU virtual cards, and MIG multi-instance GPUs. Let's start requesting a vGPU first using the default configuration. There are also some advanced configurations here. Let us expand it. You can set task priority and scheduling policies. Please note, for node scheduling policy, we'll choose spread. This means we expect this task to be scheduled dispersely, preferably onto node 02, not node 01, which already has a workload. We can also specify the specific GPU UUID or type, but let's leave that blank for now. One last check. All right, the tools here are optional, like pre-installing Jupyter. Okay, create. Let's wait a moment for the workload to start up. Okay, the status changed to running. Let's open the associated Jupyter lab. First, let's run the valigiusmi command. Yep, we can see the GPU memory matches the vGPU size we requested as expected. Now let's run a simple piece of code trying to allocate 3,500 memory first. See how the actual usage is a bit over 3,500? It's the necessary overhead for loading the CUDA context, etc., which is normal. Let each try changing it to request 4,500, run it. Look, it throws an OLM error. This confirms that the vGPUs resource isolation limits are working effectively. Excellent. Let's change it back to 3,500. Let us check the monitoring while we re-edit it. Click the workload name here, real-time monitoring data. It might take a little moment to fully populate. No worries, Let's first go back to the node list to confirm the scheduling result. Exactly. Demo 0 was successfully scheduled onto node 2, matching our expectation from the spread policy. We can also click into node 2's detail page to view its resource usage and related monitoring charts. Next, let's create another workload. We'll go through this process a bit faster. This time, enter the name demo 1, still using the default namespace in the same image. This time for the scheduling policy, we'll choose impact for nodes, which means try to stack tasks onto existing nodes. So we expect it to be scheduled onto node 1. At the same time, for the GPU scheduling policy within the node, we'll choose spread again. This means if node 1 has multiple cards, we want this new task to be placed on a relatively idle card rather than competing for the same card as the existing workload on node 01. Okay, create, waiting for it to become running. All right, let's check the node list again. As expected, demo 1 is scheduled onto node 1. Let's go check the cluster overview page. You can see the cluster says total allocated resources have increased accordingly. The data updates in real time, matching expectations. Back to the node 1 detail page. Look at this workload distribution. It clearly shows demo 1 was placed onto the other available GPU card on node 1, achieving balanced GPU resource usage within the node. We can quickly go through the GPU verification and monitoring check again, just like before. The monitoring data will show detailed resource usage for each workload. Okay, so far everything we've been on has been within this local cluster. Actually, this platform makes managing external clusters very convenient too. Let's quickly demonstrate the process of connecting an Alibaba Cloud ACK cluster. Click the Create Cluster button. Quickly input some basic info. Then the crucial part, the kubeconfig. We'll copy it from the file and paste it here. Click Validate Configure. Validation failed. Let me see. Oh, looks like I missed copying the very end part just now. Add validate again. Okay. It passed this time. Then we fill in the corresponding Prometheus address for this ACK cluster, which is used for collecting monitoring data. Confirming. All right, look, everyone, the cluster has been successfully connected to our platform. Let's click into its details. Yeah, you might see some data here already. Some from some tests I ran before starting this recording. Let's switch to the node list. Just briefly look at the node information for this external cluster. Then, just as easily, we can create workloads on this external cluster too. The process is exactly the same as before. Let's quickly create one. Once it's on running, we can view the related monitoring data just the same. Okay, so integrating and managing external clusters is that simple and straightforward. So overall, as you can see this platform through its unified multi-cluster management interface, efficient workload, lifecycle management, creation, scheduling, monitoring, and detailed resource monitoring and allocation views down to the node and GPU card level, helps us manage and utilize our GPU compute power effectively, providing a clear view of the clusterized compute status and ultimately improving overall resource utilization. This is all for today's demonstration. Thank you.